Okay, so we're here to take a look at what we call the toolbox functions and transformations of those functions. And transformations basically means we're going to shift them around and flip them over and that kind of thing. So we're going to start off a little warm-up here. As you see, we have the graph of f of x equals sine x, and we're going to do a little review here. We're going to find the range of this thing. The range of this guy here, you'll notice the bottom of this graph only goes to -1 and the top of this graph only goes to +1. So the range here would simply be, if I can draw here, -1 to 1, and since we're touching both of those, I'm going to use the brackets. The zeros here, when you hear the word zeros, those are x-intercepts, and so basically from what I can see on this graph, I see a 0 here, 1, 2, looks like 3, 4, and 5 of them. So I've got a 0 at negative, notice the scale here is not by ones, it's by -π12. So if 2 spots out, I've got a 0 at -π, so this is going to be -2π. So we would say x equals -2π, -π. We've got one at 0, +π, and +2π. All right. Intervals of increase and decrease. We'll do increasing first. So we got a whole bunch of spots where this is increasing. So we're increasing from -2π, up to -3π². So up to -3π². And we're also increasing, we come down, we're also increasing from -π². That's the bottom of that section of the graph. And we're increasing up to π². All right, up to π². And we're also increasing from 3π² to 2π. So we have one more there, 3π² to 2π. All right, so we have 3 intervals of increase. Now decreasing, we decrease from -3π² to -π². We're going down in that entire section to -π². Also, we're decreasing from π² to 3π². π² to 3π². And those are the only 2 intervals of increase and decrease. The maximum and minimum values, well, we've kind of already talked about that with the range. The maximum, the highest this graph ever goes is, so max is y equals 1, and min is y equals -1. All right, don't worry about odd even, we haven't talked about that. All right, so just a little review. Today we're going to talk, like I said, about toolbox functions. Toolbox functions are the basic graphs. Okay, so when we look at, the function y equals x or f of x equals x, hopefully you know what this graph looks like. If you don't, you can always plug in points. So, I could plug in -1. If I plug in -1 for x, I get -1 for y. If I plug in 0 for x, I get 0 for y. If I plug in 1 for x, or let's say even 2 for x, I get 2 for y. So if I needed to, I can always plug in points and I end up with this graph here. Hopefully you already knew that this was a straight line going through the origin at 0, 0. But that is what we call the parent function of a linear function. Okay? So the parent function is basically the most simple form of the function, like the second one, f of x equals x squared. That's the parent function for quadratics. Okay? So I'm going to graph a couple points on this one, maybe, and again, hopefully you've got an idea of what these guys look like already, what the shape of a parabola is, but I'm going to start with -2. I'll do -1, 0, 1, and 2. So again, if we plug in -2, -2 times -2 is 4. -1 times -1 is 1. 0 times 0 is 0. 1 times 1 is 1. And 2 times 2 is 4. So if we plot these guys, we end up with this graph right here. And again, hopefully you had an idea of the shape of this. It's just a U-shaped parabola. Okay. And absolute value next. Now absolute value might be more of a new one, or absolute value. But again, absolute value just means that when I plug a number in, no matter what I plug in, when I take the absolute value of it, it's going to be positive. So if you don't know what this looks like, again, I'll just go through and plug in some numbers here. So the absolute value of -2 is +2. The absolute value of -1 when I plug it in for x is +1. The absolute value of 0 is 0. The absolute value of 1 is 1. Okay, we're not asking you to make it the opposite. We're asking for the absolute value of it. You know, so whether it's positive or negative, once I take the absolute value, it's going to turn out to be positive. So this graph ends up looking like this. All right, so I have a perfect little V-shaped graph here, and that is the parent function for absolute value. All right. Oh, by the way, this graph has a vertex. It's got a bottom point here. It's got a bottom point that you call a vertex. It's at 0, 0. My parabola up here also had a vertex at 0, 0. That's going to be an important piece to focus on. Square root function. Okay, so if I tried to use the same t-table here, -2, -1, 0, 1, and 2, when I go to plug in -2, I get the square root of -2. We can't do that. That's an imaginary number that we cannot plot right here. So -2 and -1 don't work here. We don't want to plug negative numbers into this. Okay, we've talked about the domain of square root functions and always keeping that square root positive. So I can plug in 0. The square root of 0 is 0. The square root of 1 is 1. Now I get to 2, and the square root of 2, I'd have to take out a calculator for that. So maybe I don't choose 2, so I try and choose something easier. So maybe I choose the square root, well, 3 isn't nice, but the square root of 4 is nice. The square root of 4 is 2. If I were to keep going, I wouldn't choose 5, 6, 7, or 8. I could choose 9. The square root of 9 is 3. So I want to choose nice, easy numbers. So a square root function does this. It starts at 0, 0. It goes to 1, 1. And then we're going to slide over to 4, 2. Now we can't really graph 9, 3, but you can kind of see that this thing rolls over the top just like that. There is no bottom part. It should look like half of a parabola going in a sideways direction. And the point where it started isn't called a vertex. It's called, we just call it an initial point. And this initial point is 0, 0. All right. So these are your parent function for each of the 4 basic functions that we're going to be talking about in this section. All right. Okay. Now, the whole goal is to be able to transform these. Transform means to change in form or appearance. That can include shifting it up, down, left, right, reflecting it over the X or Y axis, stretching it, compressing it. There's all kinds of different things that we can do to these guys. But our first one is going to say to transform each of the 4 toolbox functions, we're going to do y equals f of x plus 3. So we're going to look at each of the 4 functions. So we started off with f of x equals x, and basically what we're saying is take that function right there, take x, and add 3. That's all it's saying. So this is now, you can rewrite this as y equals, or you can write it as f of x equals. It really doesn't matter. I'll probably change back and forth. So I'm going to write this one as y equals x plus 3. We're going to do the same thing here. We're going to take x squared, because it's saying take f of x, whatever f of x is, and add 3. So right now, again, we have x squared, so y equals x squared plus 3. Take the absolute value of x and add 3. So that's y equals the absolute value of x plus 3. Take the square root of x and add 3. Y equals the square root of x plus 3. Okay? So you'll notice I didn't put x plus 3 in the absolute value. I didn't put x plus 3 in the square root, because that's not what this notation is saying. This notation is saying take whatever you had and simply add 3 to the end. So that's what I've done. All right. Now, this first one should be an easy one to graph. Y equals x plus 3. We have a y-intercept at 3 here. We have a slope of 1. So I could go up 1 over 1 like this. I could go down 1 over 1. But basically, this should be a relatively easy graph. Okay? So that's what that picture there would look like. Now, in order to do some of these others, you might need a little bit of help. Some of you might know what y equals x squared plus 3 looks like. So I'm going to open up my Desmos app here on the internet, and you can see I've got my two linear equations. I've got the red one was y equals x, the blue one is y equals x plus 3. I'm going to do the same thing for x squared. Take a look at this. So the red one is y equals x squared. That's the one we graphed by hand on the front side. That's the parent. Y equals x squared plus 3 is the same graph, but the only difference being, I can pull this down, the only difference being that, you know, it's exactly the same width. Everything is the same, except the vertex has gone from 0, 0 to 0, 3. Okay? And you'll notice that if you start looking at the points here from the parabola, the first point was up 1 over 1. The second point was up 1, 2, 3 over 1. And the same thing's happening on the blue one. So it's the same width. It's the same pattern of points. It just doesn't, it just shifted straight up 3. So in this first one here, we know that this graph here, y equals x squared plus 3, is the parent function moved up 3 units. So my vertex slides up to 3, but my points, all the other points slide right up with it as well. So there is y equals x squared plus 3. Now if it helps, you can always graph the parent function on here too. Okay, so if it helps, you can graph your original parent function so you can kind of see what's going on with each one of these. All right. So that was the original, the parent function, and so you can easily see that that graph just slid up 3. Okay, and so if we look at the next one, y equals the absolute value of x plus 3, you know, maybe at this point you already kind of have a guess as to what's going to happen with this graph. So I'm going to go back to my Desmos app. I'm going to go to the absolute value of x. Again, the red one is your parent function, and the blue one is the one where we added 3. It's the same graph, just shifted up 3 units. Look at the slope of each side of this thing. The slope on the right on the red is the same as the slope on the blue. Those two are parallel. The slopes on the left with the red and the blue are the same. I didn't change anything about the graph except for sliding it up 3 units. So again, if it helps, you can plot your original function so you can see what that looks like, your parent function. All right. And then all I need to know is that that plus 3 is going to take me and bump me up 3 units. So my vertex goes up 3 units. My next point goes up 3 units. My next point goes up 3 units. Same thing on the left side. Up 3, up 3, up 3. Same graph, just shifted up 3. Okay? Now, the square root of x, let's go back and do the parent function for that guy. If you remember, the parent function started at 0, 0. It went to 1, 1, and then we actually went out to 4, 2, and it's rolling around to the right side just like that. Now, imagine bumping that up 3 units. Okay? Take your first point, shift it up 1, 2, 3 units. Take your second point, shift it up 1, 2, 3 units. Take your third point, shift it up 1, 2, 3 units. You're done. Piece of cake, huh? All right. So a transformation of y equals f of x plus 3. Okay. So y equals f of x plus 3 is a vertical shift. We call this a vertical shift up 3 units. All right? So I would encourage you at this point to stop the video and see if you can graph the four graphs of y equals f of x minus 2. Okay? F of x minus 2. All right? Now I'm going to start off with the linear equation, because again, the first one's going to be our linear. This is just y equals x minus 2. That one you should be able to graph without really any help. I mean, it's just this guy right here. It starts at -2, slope of 1. So again, you can just see that it's a slide down of 2 units. Now, I've got my parent function in blue up at the top of the screen here. So what I need to do is I need to think about what is the minus 2? It tells me I'm going to take y equals x squared, and I'm going to subtract 2 units from it. So that means that I'm basically going to shift it down 2 units. So my vertex is going to shift down 2 units. I had the 2 points that were right next to the vertex there and there. Those are going to shift down 2. And then notice the pattern of points here. This is really important. So the first set went up 1 over 1. The second points went up 3 over 1. And so now I have a graph that shifted down 2 units. All right? Same thing with my absolute value. This is now going to be y equals the absolute value of x minus 2 units. So I'm going to take my vertex, I'm going to go down 2, and then I'll drop all the other points down 2 units. And I end up with the exact same v, just shifted down 2 units. All right? And finally, my square root function, shift down 2 units, shift the first point, shift the second point, and my third point, which was at 4, 2, shift it down 2 units. So sometimes it's kind of nice at first to have the parent function in front of you so you can see what's going on. By the way, this would be y equals the square root of x minus 2. Now, notice that in each one of these, okay, a linear equation has a y-intercept, and my y-intercept here is 0, -2. My vertex on the parabola is 0, -2. The vertex on this guy is 0, -2. And the starting point on this guy is 0, -2. Okay? So we're going to be looking at these patterns here in order to easily be able to slide these guys around wherever we want to on the graph here. Okay? So in a generic sense, when we see the graph of y equals f of x plus or minus k, okay, so this could be plus or minus k. This graph is transformed k units up, when k is positive, and k units down, when k is negative. Okay? This type of transformation is a vertical shift. I tend to use the word shift, but it's also called a vertical translation. Okay? So I tend to use the word shift just because it's easier to kind of understand, and so that's what I do with those. All right? Let's take a look at the next set, see what we got going on with these guys. So now you'll notice that the transformation y equals f of x plus 3, this time the x plus 3 is inside the parentheses. So if you think about, you know, your 4 functions, we had y equals x, we had y equals x squared, these are our parent functions, we had y equals the absolute value of x, and y equals the square root of x. All right? And so now I want to do a transformation where I'm going to take, and what this notation is saying is it's saying replace x. See, in the last one we didn't replace x, we just added a 3 or subtracted a 2. Replace x with x plus 3. That's what that's saying. Anytime I see f of something, it means take out x and replace it with the something. So I'm going to take out the x here with y equals x, and I'm going to replace x with x plus 3. So this becomes y equals x plus 3. Looks the same as the last one, doesn't it? Kind of strange, but if I were to graph this, again, y-intercept at 3, slope of 1, and we have the first one. Linears are pretty straightforward. On the second one, I'm going to take out the x, and I'm going to replace it with x plus 3. But take a look at this guy. This x was being squared, so whatever I replace it with also has to be squared. That one is not the same as the previous one. If you remember, the previous one was y equals x squared plus 3. Those are two different functions there, and we'll see what they look like in just a minute here. Same thing on the next one. We're going to take out the x, and we're going to replace it with x plus 3. And then y equals the square root of x plus 3. This time the x plus 3's are inside of the operation here. Okay? So let's go take a look at the parabolas here. So we're going to go back to our parabolas here. Y equals x squared. And you can see I'm going to take off my blue one here. So I'm going to go ahead and graph y equals x plus 3. So there's my parent function. And y equals x plus 3 squared. Take a look at where that guy's at. All right, this time it didn't shift up and down. It actually shifted to the left. And as it shifted to the left, look at where it stopped. It stopped at -3. All right, so now while we're at it, well, I'm going to hold off and leave that up to you. So let's go back and let's take a look at the absolute value of x. All right, so let's take off the shift up. I'm going to graph the same absolute value of x. Y equals absolute value of x plus 3. Take a look at where it ends up. Again, it shifted to the left 3. Same slopes. Nothing else changed on the graph, just the location of that vertex. Now at -3, 0. Look at the square root function. All right, so there's my parent square root function. Here's the square root of x plus 3. Same function, just starts at -3, 0. Okay, so these first couple of shifts are pretty easy to see. So my parabola, this time it shifted 3 to the left. All of the points shifted 3 to the left. So again, if you know where that parent function is, all you've got to do is take that parent function and shift all of your points 3 units to the left. All right, so you can always peek back at some of the other ones. So this guy has a vertex at -3, 0. This guy starts over here at -3, goes up 1, up 1, up 1 over 1, up 1 over 1. Nice little V graph here. This guy also has a vertex at -3, 0. And the last one also starts at -3, 0, shifting all of the points 2 spaces to the left, or excuse me, 3 spaces to the left. I think I got that last one in the wrong spot. 3 spaces to the left, I would end up with that function right there, just like that. Again, with a starting point at -3, 0. So if you can see what's going on there, there's an obvious shift here. So I would encourage you again, turn off the video and try and graph the next 3 here. All right, so this guy is y equals x minus 2. That one should be easy. All right, like I said, linears are easy. Y-intercept at -2, a slope of 1, boom, we're done. Next one, y equals x minus 2 squared. So this one is going to take my parabola, which was starting at 0, 0, and it's going to bump it over here to 2, 0, and it's going to bump all the other points over to the right 2 spots as well. So if you look at the points from your parent function parabola that we graphed, notice the pattern here again. This is up 1 over 1 to both sides, and then up 3 over 1, and I can do that on both sides as well. The next one would be y equals the absolute value of x minus 2. So that's going to move my vertex over here to 2. I still have a slope of 1 to 1. All right. And my last one, y equals the square root of x minus 2. This is going to move my initial point to 2, 0. It's going to move my second point to 3, 1. And my next point's actually going to go off the graph a little bit, but that's okay. We'll go off the graph today. So this guy has a vertex at 2, 0, a vertex at 2, 0, and a starting point at 2, 0. I hope you're noticing the patterns of points here between where these graphs start with their vertices or the starting point and the equation itself. Notice the numbers in the vertex. All right, when I did x minus 2, my vertex changed to 2, 0. It was a shift to the right. So this minus 2 here is a shift 2 units. And really, this is a horizontal shift, horizontally. Okay? Now, I'll just say a shift of 2 units to the right. But, and again, you can see on the top one here, this top one was a shift of 3 units to the left. Okay? So, 3 units left. All right? So anytime I see the graph of y equals f of x minus h, all right, this x minus h tells me that we are transformed h units left when h is positive. Okay, so if it says x plus 3, I'm actually going to go to the left, and h units right when h is negative. Okay, just like in the 2 examples above there. This type of transformation is a horizontal shift, or horizontal translation. So I'm just going to say right and left. I don't really care about using the word horizontal. I just need to know that it goes to the right or to the left, and when it goes to the right or to the left. Okay? All right, let's take a look at the next one here. All right, this time we have y equals the negative of f of x. So what this is saying is take your function f of x and just toss a negative in front of it. Okay? So if you think about y equals x, okay, here's my 4 parent functions again, y equals x squared, y equals absolute value of x, y equals the square root of x. All right? So all that's saying is put a negative in front of each one of those. So now I would have y equals negative x. Okay, well that should be relatively straightforward. It has a y-intercept at 0, 0, so it starts at the origin, but instead of going up 1 and 1 to the right, it goes down 1 and 1 to the right, so it has a negative slope. So on a linear equation, all that negative does is change my slope from positive to negative. On a parabola, y equals, all I'm doing is I'm putting a negative in front of the function itself, so I have y equals negative x squared. My absolute value is going to be y equals negative absolute value of x, and y equals negative square root of x. Okay, so let's take a look at these guys. We'll go back to Desmos here for a minute. I'm going to go back to my x squared function. We'll take off that guy, and we'll put in a negative x squared. And look at that. Same parabola, it just flipped over, right? We actually call that a reflection. Okay, it reflected over the x-axis. Let's take a look at the absolute value. We'll take off that guy, put in the negative. Same thing. It just reflected. It flipped over the x-axis. Square root function. Take off that guy, put in the negative. Oh, now this one's kind of interesting. It's still reflected. Notice the points that reflected. The 0, 0 stayed in the same spot. But, you know, this point at 1, 1 is now at 1, negative 1. This point that was at 4, 2 is now at 4, negative 2. So it's still flipped over the x-axis. Okay? So these guys are reflections. Okay? This type of transformation is a reflection over the x-axis. Okay? In other words, if I throw a negative out in front of my function, all my y values change to opposite numbers. None of my x values changed. Only my y values changed. So my parabola that was going up now just goes down. Same pattern of points. Down 1 over 1. Down 3 over 1. Down 3 over 1. It's just an upside down parabola. That's all it is. My absolute value that was going up with a slope of 1 to 1 still starts at 0, 0, but it goes down with a slope of 1 to 1. All right? And my square root function, which was going up and curving to the right, is now going to go down and curve to the right. Just like that. So a negative in front is a reflection over the x-axis. All right? Let's take a look at a negative inside. All right? This one's an interesting one. So now what we're saying again is, and again I'm going to write this out because this is important that you understand this. Replace x with negative x. Okay? I want you to think about that as I start to write these out. So I'm going to write the parent functions again. This was y equals x. This was y equals x squared. Oops, what happened here? See if we can fix that. Y equals x squared. This was y equals the absolute value of x, and this was y equals the square root of x. Okay? So those were my functions, and let's take a look at what happens when we replace x with negative x. So if you look at the linear function, if I take out the x and replace it with negative x, I still get y equals negative x. Well, we just got done graphing that one. So the linear function doesn't change when I replace x with negative x. I still get a y-intercept at 0, 0 and a downward slope of 1 to 1, just like that. All right? The next function, you got to be careful again, because when I take out x, whatever I replace it with has to be squared. So when I replace x with negative x, I have to have parentheses around that. And you'll see what's going to happen here in just a minute when we look at the graph. But that x has to be squared. So whatever it gets replaced with has to be squared. Y equals the absolute value of negative x. All right? Think about that one for just a second before we go on. What happens when you take the absolute value of anything, positive or negative? It always comes out to be what? positive. So no matter what I plug in for x here, it's still going to be positive. Whether it's 1 or -1 or whatever, it's still going to be positive. Think about what that's going to look like. And then y equals the square root of -x. And then your first thought is probably, oh, well, that's not going to work because now x is negative and you can't have negative square roots. That's true if I plug in positive numbers. If I plugged in +1, it wouldn't work. All right? But think about this. Just for a second here, I'm gonna actually do a little t-table for this one. All right? Now, if I try 1, it doesn't work. I can't do that. No, not gonna work. Yeah, done. Because I can't take the square root of -1. What about 0? Well, -0 is still 0, so I can do that. That works. I can't plug in +2 or 3 or 4 because they would end up being negative. What about a -1? If you plug in -1 for x, it becomes -1, which is +1, and the square root of +1 is 1. Now, I'm going to go to some easy numbers here because I don't want to do 2 or 3, so let's just jump ahead to -4. A -4 is +4, and the square root of +4 is 2. All right? So let's take a look at this graph. Still starts at 0, 0, but my next point is -1, 1. My next point is -4, 2. Do you see what's happening here on this one? Let's go to Desmos and take a look at these with their parent functions. All right? So let's take off this guy and put in the other one that we just graphed. So my parent function moves up and to the right. My other function moves up and to the left. Okay? So this guy on the right has flipped over the y-axis this time. Not over the x-axis, but over the y-axis. Take a look at the absolute value. Okay? Here's the one we're about to graph. Nothing changed here, did it? Remember I talked about the fact that if I plug in anything for anything for x, whether it's positive or negative, the absolute value is always going to be positive, which means no matter what I plug in for this function here, it's going to match the parent function all the time. It doesn't matter. Okay? And my parabola, here's y equals -x squared. Same thing. You get the exact same function back. Now, the reason that these two look the same, so let's go back and graph these and then we'll talk about these. So my absolute value looked exactly the same. Okay. My parabola looked exactly the same. But my linear equation didn't look the same and my square root function didn't look the same. So something has to be going on here. You can't say if I put a -x in, sometimes it affects the equation, sometimes it doesn't. Now, it doesn't affect the way the graph looks, but it does actually affect the equation, okay? And it's easiest to see on the square root function. The original parent function here went up and to the left. So it came up and around to this side. This was my parent function right here, okay? This was parent. The red graph has reflected over the y-axis this time. Last time it was easier to see because the reflection was over the x-axis. This time it's reflecting over the y-axis. So if you think about it, if I take this parabola, if I take the right side of this parabola and I reflect it over the y-axis, it ends up laying on top of the left side of itself. Okay? So hopefully you can kind of see that in your head there, what's going on there. But this type of transformation is a reflection again. It is a reflection over the y-axis. All right? So sometimes you can have a reflection where the graphs look the same, and sometimes you can have a reflection where it does look like a different graph. Kind of like our linear equation. It's the same thing. It's a reflection over the y-axis. If you reflected these points back, you would end up with the parent function again, just like this. Okay? So it is actually reflecting. So what happens here is all the x values change to the opposite. All right? And again, you can notice that the graphs of f of x equals x squared and f of x equals the absolute value of x, those are going to stay the same. Okay? All right. So, what do we have next here? All right, so we got another type of transformation going on here. All right, this time we're going to take and we're going to multiply each function by 2. So just like when we put a negative in front of each one of these, now it's saying put a 2 in front of each one. So my first one would be y equals 2x. My next one would be y equals 2x squared. My third one would be y equals 2 times the absolute value of x, and y equals 2 times the square root of x. All right? So y equals 2x, again, that one should be relatively straightforward to graph. It's still got a y-intercept at 0, 0. This time, though, the slope is up 2 over 1. Or you could go down 2 and left 1. So this graph got a little bit steeper than the parent function. Remember, the parent function had a slope of 1 to 1. This guy now has a slope of 2. So it's a bit steeper. Let's take a look at some of these other ones on Desmos here. All right. So let's get rid of this guy. Now there's my parent function again, and here's y equals 2x squared. Notice the vertex is in the same place, but the graph got skinnier. Okay, it got skinnier. So, and as you look at it, I want you to take a look at some of these points here. Notice this first point was at 0, 0, and then on my parent function, the next point, full numbered point, was 1, 1. But now this next point is 1, 2. All right. Now this is kind of important that you see this. On the parent function, my next point was 2. Where are we at here? There's 2. My next point was 2, 4. Look at where it's at on the blue function. 2, 8. It's twice as high as the previous point. Same thing on the left side. Each point from the red to the blue points are twice as high. Take a look at the absolute value of x. Let's take off that guy, put on this one. Notice the vertex is in the same spot, but what do you notice about the slope of each side now? The red graph goes up at a slope of 1 to 1, up 1 over 1. The blue graph now goes up at a slope of 2 to 1, and then up 2 over 1. Okay? So what we're doing is we're stretching the graph. We're multiplying the y values by a factor of 2. Take a look at this point right down here at 1, 1. Okay? Well, I have a point on the original parent function at 1, 1. Now, if you multiply the y value by 2, 1 times 2 is 2. Go to the next point. On the parent function was at 2, 2. If you multiply the y value by 2, it's 4. So what it's doing is it's taking and it's multiplying my y values by a factor of 2. All right? Look at my square root function. Before I put it up, let's take a look at my first point. My first point was at 1, 1. If I multiply the y value by 2, that means that new point should be at 1, 2. Go to the point 4, 2. 4, 2. Multiply the y value by 2. 2 times 2 would be 4. It should be up here at 4. Let's take a look. There you go. The point that was at 2 is now at 4. The point that was at Where's 1? At 1 comma 1 is now at 1 comma 2. So this is a multiple, okay? This is what we would call a vertical stretch. So it doesn't change the location of the vertex. So my vertex on my parabola stayed the same. The vertex on my absolute value stayed the same. The starting point on my square root function stayed the same. Why do they stay the same? Because when you multiply the y value by 2, the y value is 0, and 0 times 2 is still 0. But it did take, and I'm going to very lightly plot, see these 2 points here, I don't know if you can see these very well. If I multiply the y value by 2, it stretches up 2. If I multiply the y value by 2, it stretches it up to 2. My next points, I'm not even going to be able to fit them on the graph, but the next point was 2 comma 4. If I multiply that by 2, it's going to be way up here at 2 comma 8. So this graph got much skinnier by multiplying it by a factor of 2. The absolute value graph changes the slope. On the right side, it's up 2 over 1. On the left side, it's a negative 2 over 1. Same exact vertex, just a different slope. Okay? And the tricky one is going to be the square root function, because you have to know where was the parent function. So I had 1, 1, I had 4, 2, and again, we're multiplying the y values. We're keeping the x values the same, so the y value is 1. 1 times 2 is 2. The y value is 2. 2 times 2 is 4. And there's the curve right there. Okay? So this graph, this is a vertical stretch. All right? And I would encourage you to turn off the video again at this point and see if you can do y equals 1/2 of f of x. Okay, so here we go. Our first graph is going to be y equals 1/2 x. So again, that should be relatively straightforward. Starting at 0, 0 for the y-intercept. This time we're going up 1 and over 2. Up 1 and over 2. So this has less of a slant than the parent function. Y equals 1/2 x squared. Y equals 1/2 absolute value of x. Y equals 1/2 square root of x. Now I'm going to start off with the absolute value here because, again, if anything up top made sense here, then you'll know that the vertex is going to be the same. And if you notice that the slope changed according to the number in the front, then the slope on this guy would be up 1 and over 2. Up 1 and over 2. So an absolute value function, this number in front, this is the slope of one side. Okay, so I usually say the slopes are plus and minus 1/2. On the right side of this, it's positive 1/2. On the left side of this, it's negative 1/2. So I would have a graph that looks like that. Okay, now, as I look at the other two, the vertices didn't move for the parabola. The starting point didn't move for my square root function. But instead of multiplying my y values by 2, this time I'm multiplying my y values by 1/2. So instead of having a point here at 1, 1, I need to cut that in half. I'm going to have a point at 1, 1/2. See if I can get that on there. Right there. That means I'm going to have one on the other side at 1, 1/2. My other point, my next point on my parent parabola was at 2, 4. So it should be halfway there, 2, 2. And that means I should have one on both sides. So you'll notice this graph just got a bit wider than the other one. Let's take a look at Desmos here. All right, I'm going to leave that guy up. Let's go to the parabola here and take a look at both of these. Look at the green one there. It's wider than the parent. The parent's the red, so it's wider. And basically what it's done is it's taken the red graph and it's multiplied all of the y values on the parent function by a half. And you can see that on the parent function I had a point at 2, 4. Now that point is at 2, 2. All right? Same thing with the square root function. I'm going to leave them both up there this time. Look at the square root function. It took all of your y values. You had a point at 1, 1. Now that point's at 1, 1/2. You had a point at 4, 2. Now we have a point at 4, 1. Okay? So this is taking the y values and multiplying them by a half. So my square root function now looks like this. It's halfway to what it used to be. All right? So this graph is a vertical compression. All right? This is a vertical compression. It's being pushed down. Okay? That's all that's happening is the points, the key point, the first point on the parabola, the vertex or the starting point or the y-intercept doesn't change. All it does is it pushes all of the other points down half the space that they used to be. All right? This graph of y equals a times f of x is transformed by stretching the graph I should say by stretching the parent graph, okay, because that's the key. We're always looking at the parent. By stretching the parent graph by a multiple of a. Okay, when I say a, I'm talking about that a that's out in front, a times f of x. Okay? By stretching the graph by a multiple of a units, and I shouldn't stop there with my period. By stretching the graph by multiple of a, when a is greater than 1, so if it's anything over 1, it's going to pull the points up, okay? Or by compressing the graph, when a is less than 1 but greater than 0. So a has to be between 1 and 0 for it to push down. If a goes into a negative, then remember it flips it over. It does some other stuff there. Okay? So this type of transformation is a vertical stretch or compression. Okay? And so what we want to be able to do is we've now looked at like 4 different things. We want to be able to put all of these things together and graph them all at once. And that's what we're going to take a look at on this last page here. So let's take a look at the key parts. So putting all of these parts together, okay, we talked about what happens when we put a plus or a minus k in the back. We talked about what happens when we put a plus or a minus h in the middle. We talked about what happens when we put an a value in the front or a negative in front of the x. Ooh, yeah, that one was the interesting one. Oh, I might want to plug in my PC here. Uh-oh. I think I might be in trouble here, guys. Hang on. Okay, so we're going to call it quits there. I'll do the second part on another video.